So let's start our discussion on DMA. So why we use DMA? Because there is every time CPU has to involve in each of the word transferring between the device and the our final memory. So that means every time CPU is involved between them, CPU has to have the all attention there. That is, if I'm copying 10 MB file, that means each of the word has to be transferred from this IO device disk to the memory, and it has to go through the CPU. That is, CPU would act as a middleman here. So what does this DMA do is that DMA is a module which is placed in our system bus, and it is close to our CPU and memory. Now it helps us to transfer the data between the IO devices and the memory on its own. That means there is some dedicated registers which is present in this DMA, and also it can take the control of the bus to transfer. So there is no CPU involved. DMA can transfer the data between the IO device and the memory. So here, when the CPU wants, if let's say a block of data transferred, it issues one-time command to the DMA module and walks away. The command contains exactly 4 pieces of information, whether this is a read or write operation, the address of the IO device, the starting memory address where data should be read from or returned to, and the number of words to transfer. Once the CPU has handed over these details, it is completely free to go. So what does the CPU tells? What are the details that the CPU is giving to the DMA? It will give only a command. One time it will give a command to whom? The DMA. This command, it would include which IO device I have to read or write. Whether first it is whether I have to read or write. Right, whether I have to read or write. First command, first thing in the command. And the second thing in the command, from which device? The IO device's address. Then in which location of the memory whether I have to read or write. Memory address. Right, then the final thing that it has to give is how many words I have to transfer, how many words, how many number of informations I have to transfer. So these things are included in the CPU command when it is giving to DMA, and after giving this command, the CPU is now free to go do any other task. So that means after giving this command, the CPU has now become what? Free. Right, the CPU has become free. Fine. So now let's see how the data transfer happened. That is, we are talking about cycle stealing. The DMA now takes over, and it would transfer the data one word at a time directly between this IO device and the memory, bypassing the CPU entire, means not involving the CPU, right? But there's a physical constraint. Both the CPU and DMA share the same system bus, but only one of them can use a bus at the time. So that means that is called as cycle stealing. Here what happens is that the DMA is now taking over the control, and it will transfer each word of data from the IO device to the memory. Now this CPU and the DMA is both sharing the same system bus. So sometimes one time only CPU can access it. Right. So how do CPU and DMA share the system bus? So DMA resolve this through a technique which is called as cycle stealing. The DMA watches the bus and grab it during the moment when CPU isn't using it, typically between CPU's instruction cycle. The DMA would steal one bus cycle, transfers one word of data, then release the bus. The CPU may slow down slightly because occasionally it finds the bus occupied, but it never stops completely. Meanwhile, the DMA is steadily chipping away at the transfer one stolen cycle. That is, one cycle is stealed. One bus cycle the DMA would steal. When it finds out, it will always watch this bus, and it would grab that bus when it finds out the CPU isn't using it. Maybe it will be going and fetching one instruction. It will be typically between some instruction cycle and not at the time where it requires this bus. So it will steal that. So the CPU can become slightly delayed because of this, but it's fine because only CPU can occasionally get the bus again, right, after transferring one word. So here one bus cycle is being stealed by the DMA. So that is why it is called as cycle stealing. Okay. Now, when the last word of the block has been transferred, the DMA module would send a single interpret signal to the CPU. This is the CPU's suit to come back and use the data. The CPU was interpreted just one at the very end rather than the word per word as in interpret driven IO. By the time CPU receives, all data is already sitting in the memory and ready to see. After completion, what happened? A single interpret, after all the data has been transferred, only the DMA would give a single interpret to the CPU. So the CPU will know that all the data is now there in the memory. So the CPU can do other tasks, like rather than one, because here after each of the word the CPU would get interpreted in interpret driven IO. But here by the time CPU is receiving all the data, resume its work, all the data is already sitting in the memory and it is ready to use. That is the thing. So consider transferring 10,000 words from disk. With interpret driven IO, the CPU would be interpreted how many times? 10,000 times, once for every word, executing dozens of instructions each time. With DMA, the CPU is interpreted only one time. The CPU would DMA would handle all these 10,000 words independently. So the CPU is free to run other program and will handle other tasks or simple execute more useful work during that time the transferring is happening. So for large data transfer, discrete network, video buffers, DMA is not just faster, it is transformatively more effective. So very efficient, right? For larger transfer and all, DMA is a more efficient solution. Fine. So here if we see, this is the typical DMA block diagram. So in this DMA block diagram, we have the control logic, the data count, the data register, the address register. Now this control logic is something which is the request to the DMA from the CPU would come to the control logic, and the control logic would later send the interpret or acknowledgement from the DMA and all is given from here. Now read write signals are all going to this control logic. So through this DMA everything, now they have address register and data register, address line and data line, it is connected. And how many, we know it will tell how many data is there, data count, how many data has to be transferred, that is data count, that is also we have to understand. So in the typical here, if you are giving a request to DMA, that is going to the control logic, and that request contains lot of things, and also acknowledge from DMA, interpret can also come from DMA. Now whether you have to read or write, these things are also given to the control logic itself. Now data register and address register is connected to the address line. Understood? And also it will count the data count, that means how many data, how many addresses given, that means that many data count will be there, that many data we have to transfer between the IO device and the others. So acknowledge from DMA and interpret are given out from the control logic, and the request is given to the DMA. Okay, now whether we have to read or write, that also is should be given. Fine. Now if you see here, interpret DMA and interpret breakdown during instruction cycle, if you see, these are the different processor cycles. Okay, so what happens here we will be understanding, that is this small example is given here. Here's a breakdown of cycle stealing and DMA. This we will understand what is happening here. Okay, we will understand that. Now see this here, this is a breakdown of cycle stealing and DMA configuration in this image. So here if you see how the cycle stealing is happening, where the processor is suspended for cycle stealing. Here we know fetch is the decoding, executing, write back, DMA steals one bus cycle. This is not a interpret, no contest, no jump, nothing is here. The CPU simply pauses here for one bus cycle, then resumes that. That means when the processor is where the processor is suspended for cycle stealing, where the DMA is stealing one bus cycle, so it can get suspended in the, that is after fetch point there is a suspend, after execution and after write back there is a suspending point. So here just one cycle, one bus cycle is just stealed, there is no interpret happening here. Now DMA configuration, if you see, there is different single shared buses there with IO. This also we will learn later, because we have a detailed image of that here. How is the DMA's different configuration, that we have to understand in detail. Okay, so these are the different suspend point after fetch, after decode. So here if you see, processor is doing this one in one processor cycle, fetch instruction, another processor cycle decode, like is happening here, then executing, then store the result and process the interpret. So here DMA breakpoints can happen in the fetch, decoding and executing part, right? This is DMA breakpoints. But if it is in the case of interpret breakpoint is happening after the store result. Then it will do interpret, then it will process the interpret. After the complete instruction finish, the interpret would come and then it will process the interpret. So interpret breakpoint, that is here the DMA breakpoint, means the DMA is asking for that one cycle to transfer. Then later the last interpret would become only after the result and all is stored. After the final result and all is stored, then the interpret breakpoint would come. Then only the CPU would go to process the interpret. Understood? So in our total instruction cycle, we have the fetch instruction, decode instruction, fetch the operand, that is decoding, and we have to understand here in the fetch instruction, decoding instruction, then fetch the operand and execute the instruction. So in this executing, decoding the instruction, after the decoding instruction, fetch instruction, these are the DMA breakpoints. Then after storing result, then we have interpret breakpoint. Final, after result and all is finally stored, then we will go and process the interpret. Understood here? Now here if you see, the key insight here is that the CPU does not use the system bus in every single clock cycle. No, the instruction cycle has phase: fetch, decode, execute, write back, and during some of these phases like decode, the bus sits idle. So the DMA module watches for these ideal gaps between these, right? So the moment the CPU is about to need the bus for the next phase, if it requires a bus, the DMA quickly requests it, transfers exactly one word of the data, then release the bus before the CPU even notices the wait for longer than usual. So that means there are different stages, and in some stages like those phases, let's say in after the decoding, maybe the CPU would sit idle. At that time, when the bus is sitting idle, because of the decoding time, the CPU is sitting idle, because not CPU, the bus would sit idle. So it will see when there is idle gaps. That time the DMA would watch for this idle gaps, and the moment the CPU is about to need the best for the next, the DMA would quickly request it and transfers the word. Okay, so this is the fundamentally different from an interpret. In an interpret, CPU saves its entire context there and jump to a different routine, complete it and restore the context, right? So in cycle stealing, it's just happened, the CPU simply just waits one extra clock cycle at a bus boundary. That is only what has happened. There is no counter save, there is no jump, there is no restoring like interpret IO. The CPU resumes from exactly the same point with zero awareness than anything happened. It won't even notice it. That is the main thing. Before it notices itself, it will give the system bus back. DMA would give the system bus back. So the only side effect to the processor is that it will run slightly slower overall, because it occasionally has to wait an extra one cycle because it is stealed by our DMA, right? So there are three configuration here. That is the next thing that we are understanding here. That is, there are three configuration. So here, if you see, I hope you have understood this image. That is this image. This is the typical block diagram of the DMA. Then we have to understand this image. This is the points, DMA breakpoints and interpret breakpoints in our instruction cycle. Okay, instruction cycle will fetch instruction, decoding the instruction, fetching the operand and executing the instruction, then storing the result, then process the interpret. This is all thing which is happening here. So I hope you have understood this diagram. Now we are going to talk about the three important DMA configurations. So these are the three important DMA configuration here. That is, this is single cycle detached DMA, single cycle integrated DMA IO, and this is the IO bus. So these are the different configuration. So we have to understand these configuration. Let us see. In the configuration 1, you have a single bus, right? You have a single bus. Single bus is there. If you see the configuration 1 image itself, you can see that there is a single bus like this. Wait a minute. There is a single bus like this. Okay. So we have our processor, DMA, then lot of IO modules will be there, and then you have the memory. So here what happens is that it is the simplest to build but the most inefficient to run. Here all components CPU, DMA, memory and all the IO devices is shared in one bus. When the DMA transfers a word, it first reads it from the IO device onto the bus into its own internal buffer, then writes it from its buffer out to memory. Every single word goes 2 full bus cycles. The bus is occupied twice as long it needs to be, and the CPU is frozen out twice per word. So the textbook correctly codes is clearly inefficient. So that means the first configuration you can see there is only a single